In this video, we are going to look at quantum physics, starting off with energy of a photon and ending up with the photoelectric effect. Now, evidence for the existence and energy of photons comes from the way electromagnetic radiation interacts with matter in the photoelectric effect and in the existence of line spectra. A photon is a tiny packet of electromagnetic radiation of a certain frequency or wavelength. Sometimes it is considered as a particle. So the energy of a photon is proportional to the frequency of the electromagnetic wave, and a photon travels at the speed of light in the medium. So the energy of a photon is given by E is equal to hf. E is the energy, h is Planck's constant, which is 6.63 times 10 to the power of minus 34. F is the frequency. Now, since we know from the wave equation v is equal to f lambda, since we are using the speed of light, v changes to c, so c is equal to f lambda. Therefore, we make f the subject so that we get c over lambda. So instead of writing hf, we write hc over lambda. So this equation is called the Einstein Relation, which gives us the relationship between the particle property energy E and the wave property, that is the frequency or wavelength and the speed. Intensity at a particular point is defined as the power through a unit area at right angles to the direction of propagation. Okay, so power over area is intensity. So power crossing a surface divided by the area. Now, since you know that power is equal to energy over time, so it's energy per second divided by area. So energy per second over the area. Now, if we find the energy of one photon, like we said, hf, we need to multiply by the total number of photons and then divide by area times time, since here we said energy per second, so energy over time. So photon energy per time per second divided by the area times the total number of photons, so that we get the total energy of the photons. Intensity is measured in watts per square meter or joules per second per square meter. The number of photons arriving at a point is a measure of the intensity. So the intensity at any point is the photon energy multiplied by the number of photons arriving per unit area per unit time. It is often clearer to write energies in electron volts rather than in joules because the energy values are very small in joules. So 1 eV is the energy gained by an electron when moving through a PD of 1 volt. Remember, whenever we have a charged particle being accelerated by an electric field, we use QV as our formula. So QV will be equal to the kinetic energy that it is given. So in this case, 1 EV is equal to 1.60 times 10 to the power of minus 19 joules, because the charge is 1.60 times 10 to the power of minus 19 coulombs, and the PD is 1, so it's supposed to be minus. Yeah, that gives you that energy there. Now let's look at examples. Example number 1. Calculate the energy of a gamma ray photon of frequency 10 to the power of 26 Hertz in joules and in EVs. Now remember, we apply the formula E is equal to hf to get the energy. So h is Planck's constant, 6.63 times 10 to the power of minus 34, and then the frequency is 10 to the power of 26. If you do the maths correctly, you get 6.63 times 10 to the power of minus 8 joules. Now, since 1 EV is equal to 1.60 times 10 to the power of minus 19 joules, we make simple proportion here. Say, what about this energy, 6.63 times 10 to the power of minus 8 joules? What will it be in EVs? Obviously, you get 6.63 of minus times 10 to the power of minus 8 over this value times 1. Then your answer should be 4.14 EVs. Question number 2, example 2. Red light has a wavelength of 700 nanometers, while violet light has a wavelength of 400 nanometers. Calculate the energies of photons of red and violet light, both in joules and in EVs. So the energy will be equal to HF or HC over lambda. So HC, that is 6.63 times 10 to the power of minus 34, times C, which is 3 times 10 to the power of 8, over the lambda, which is 700 nanometers. Should get this one, 2.8 times 10 to the power of minus 19 joules. Now in EVs, we use the simple proportion that I talked about. If 1 EV is this, what about this value here? Simple proportion, then that gives you 1.8 EVs. Similarly, for violet, you find energy is 5 times 10 to the power of minus 19 joules, and in EVs, 3.1 EVs. Please write the comments if you have managed to do it. If you haven't managed to do it, please let me know and help in any way I can. Number 3, a 1 milliwatt laser produces red light of wavelength 648 nanometers. How many photons does it produce per second? We first of all calculate the energy of the photon. Okay, so it's going to be hc over lambda, Planck's constant 6.63 times 10 to the power of minus 34 times c, which is 3 times 10 to the power of 8, divided by this 648 nanometers. Please remember to convert it to meters as well by multiplying by 10 to the power of minus 9. Now when you've done that, we know this is the energy of one photon. Now we have got so many photons producing this, right, which has this power. Remember, power is equal to energy over time. So this is going to be 1 milliwatt, which is 1 millijoule per second. So 1 times 10 to the power of minus 3 joules per second. So you divide this by this energy that we found here for the energy of a photon to get the number of photons that are produced per second. So if you do that, that's this 1 times 10 to the power minus 3 divided by the energy that you found here. You should get 3.3 times 10 to the power 15 photons per second. Please let me know in the comments if you managed to work it out. And then the last question, energy from the sun strikes the Earth's surface at a rate of 1000 watts per square meter. What rate of arrival of photons is this? Again, you do the maths here. You take the average wavelength of sunlight to be 500 nanometers. So it will be hc over lambda, the energy of this photon of light, of sunlight. So it's going to be hc 6.63 times 10 to the power of minus 34 times 3 times 10 to the power of 8 divided by 500 times 10 to the power of minus 9. When you do that, you then say, so this is the energy of one photon of sunlight. Now we want to find the rate of arrival, which is going to be this 1000 divided by that energy that you found per square meter. So it's going to give you 2.5 times 10 to the power of 21 photons per square meter per second. Please let me know in the comments section if you do not get these values that have presented as your answers. Now moving on to the last bit, that is the photoelectric effect. Now this is the emission of electrons from some metal surfaces when electromagnetic radiation of high enough frequency falls on the surface. The emitted electrons are called photoelectrons, but they are identical to any other electron and have the same specific charge E over m. The effect can be demonstrated as shown using the gold leaf electroscope. Now the electroscope discharges when the electroscope is negatively charged, and ultraviolet is used to illuminate the freshly cleaned zinc plate. We have the gold leaf there. In the initial position of the gold leaf, you charge it up, and then if you have ultraviolet coming in, then the leaf will fall. Okay, the leaf will fall. The electroscope discharges, meaning that we have liberated some electrons from the surface, so we have less negative charges remaining, therefore less repulsion on the gold leaf electroscope, and therefore the leaf drops. If the intensity is increased by bringing the ultraviolet lamp closer to the plate, the electroscope discharges more quickly. The electroscope does not discharge when the electroscope is positively charged. That is, so you won't have anything leaving the surface if it has been charged positive. Nothing leaves the surface. Only when it is charged negative, it means we are losing some negatively charged particles from the surface going away. So that gives evidence to this photoelectric effect. Electrons require more energy to escape, and the radiation does not supply enough energy. A sheet of glass is placed between the UV lamp and the zinc plate because glass absorbs UV, right? So a tungsten filament lamp is used because it does not produce UV. Experiments on the photoelectric effect show the following results. For any metal, no electrons are emitted if the frequency less than a certain value, which is called the threshold value. So if the frequency of the incident radiation is below a certain threshold frequency, if not, there is no electron that is going to be emitted from the surface, even if the light is very intense. Weak UV can emit electrons from zinc, but very intense IR cannot, because its frequency is low. Above the threshold frequency, if not, maximum kinetic energy of the emitted electrons increases with the frequency of the incident radiation, but is not affected by the intensity. Even dim light gives some electrons with high kinetic energy. Then increasing the intensity of the incident radiation increases the number of photoelectrons emitted per second. The emission is instantaneous. However, weak the intensity is. The threshold frequency for a given metal is the minimum frequency of electromagnetic radiation for which photoelectric emission occurs. Problems with the wave model explanation of the photoelectric effect. The wave model cannot explain why the threshold frequency is there. Emission ought to take place whatever the frequency, because each electron in the metal would absorb some energy from the incoming waves and gradually gaining enough energy to escape. The wave model does not explain why the kinetic energy of the emitted electrons depends on the frequency of the incident radiation and not on its intensity. Increasing the intensity increases the energy falling on the metal, so the energies of the emitted electrons should increase. Also, the wave model does not explain why the emission is instantaneous. No matter what the intensity is, if the light intensity is low, no single electron gains sufficient energy to escape. At least it would take some time before an electron escapes. Now, Einstein's explanation of this photoelectric effect. The photoelectric effect can be explained by assuming that atoms can only absorb light energy in discrete energy packets or quanta code photons. The energy of a photon is given by HF. Now, these photons do have different energies. A photon for IR has a different energy because its frequency is low. A photon for UV has high energy because its frequency is high. So a photon of IR, the energy is insufficient to cause photoelectric effect. So we would need a photon of UV. So that photon of UV has high energy, no matter if its intensity is very low. Photons are indivisible, so each photon gives all its energy to one free electron in the metal during the interaction. So multiple collisions of photons with one electron to acquire the energy are not allowed. So photon knocks out an electron. One photon, one electron. Electrons that are more tightly bound below the surface have less kinetic energy than the maximum value because they need more energy to be released. The fastest moving electrons are those that are least tightly held in the metal, that is, those that are near the surface. Increasing the intensity increases the number of photons arriving per second. So intensity has something to do with number of photons arriving per second, so more photoelectrons are released. There's no time delay because electron emission is the result of a direct collision between electron and the photon. The diagram summarizes the explanation. So there you are. So if the energy HF is less than the work function, now the work function is the minimum energy required for photoelectric effect to take place, or the minimum amount of energy required to remove an electron from the surface. So if this HF is less than the work function, no photoelectric effect takes place. If this energy is just equal the work function, then you just have electrons being knocked off. And then if this energy is way greater than the work function, then you get these electrons given a kinetic energy to leave the surface. Right, so the photon energy is greater than the work function, so they've given a maximum value of kinetic energy. Einstein's equation for the photoelectric effect, therefore, is HF is equal to work function plus half mv squared maximum. But remember, this work function is equal to HF naught, right? Planck's constant times the threshold frequency. So HF naught plus half mv squared is equal to HF. So for HF, that is the work function, there is no kinetic energy, so it's plus 0. That's why I have a plus 0 there. Now let's look at these examples and then we end this video there. The work function of zinc is 6.9 times 10 to the power of minus 19 joules. Find the threshold frequency. So threshold frequency, so we know E is equal to HF naught. So threshold frequency will be E over H. So that will be that value there divided by 6.63 times 10 to the power of minus 34. Number 2, the work function of zinc is 4.24 EVs. What is the maximum wavelength of light that can cause electrons to be emitted from a zinc surface? So first of all, convert the EVs to joules by multiplying by 1.6 times 10 to the power of minus 19. And then you then divide by H to find lambda. Just check that you get the answers that are written there, 293 nanometers. If not, then let me know in the comments. Number 3, a metal surface with a work function of 4.0 EVs is illuminated by light of wavelength 200 nanometers. What is the maximum velocity of the photoelectrons produced? So we now use the full equation. HF is equal to work function plus half. You convert these EVs to joules, and then when you've done that, that will be your work function. Okay, that will be your work function. And then HC over lambda will be equal to your HF there. And then to find maximum kinetic energy, it will be HF minus work function. Please make sure to leave your answer in kilometers per second so that you can compare. Right, so I'm going to end this video here. Signing out.